Hi everyone, I promised to give you a video tutorial of match pairs and difference between two population proportions. We're going to start off with match pairs, where the two samples that we have obtained to test for the difference between population means happen to be matched in that the individuals or the elements that provided the data in one sample are the same elements that provided the data in the other sample. It's kind of like a before and after situation. So if you have a group of individuals that you tested before a situation and then after a situation, you tested the very same individuals, you get two values from each person. That is referred to as matched values or pair values that are matched to each other. Or you could also refer to it as an experiment for which you are repeating the process. So if you ask me to type something before I got trained and then ask me to type again, you're repeating the process. So we call it repeated measures or we call it matched pairs. All right? And the two samples, we also refer to them as dependent samples. Those two samples are dependent on the very same individuals or the same elements that provided the data. So let's start off with one problem from our textbook. And that problem, you could also find it in workbook D. All right? So let's take a look at that particular problem. So here we go. So we have, according to this problem, the Global Business Travel Association reported domestic airfare for business travel for the current year and the previous year. And that was in February 2012. Below is a sample of 12 flights with their domestic airfares and shown for the 2 years. So, excuse me, we have the data in the table. Current year 345, previous year 315, 526 versus 463. So these are 12 flights, and we're looking at the previous year and the current year. And so therefore these two values are matched values. They have something in common, that is the particular flight number, whatever that is. Formulate the hypothesis and test for a significant increase in the mean domestic airfare for business travel for the 1 year period. What is the p-value using a 5% level of significance? What is your conclusion? So they want you to test if there's been an increase or if the increase is significant between the current year and the previous year. What's the sample mean domestic airfare for each year, and what is the percentage change in the airfare over a 1 year period? The percentage change would simply be the value for the current year divided by the average for the previous year. Average for the current year versus the average for the previous year. All right, so let's work this problem and see if we can set up these hypotheses. All right. Excuse my cough, it's still there. And so here we go. So the first thing we're going to do is we're going to take those two sets of values and calculate for them a difference. All right? So we could refer to that difference as DI, the difference. So what's the difference between 345 and 315? There's a $30 difference and so on. So we're going to do that. So I'm going to actually do that in Excel to calculate those differences, and then I'm going to need the sample mean of the differences. I'll need the sample standard deviation of the differences. And then of course we could always find the standard error, SD over the square root of N, and that's for 12 flights, whatever that turns out to be. So we will have these three pieces of information, and we could calculate t-value, confidence interval, whatever we need to calculate. We're going to define mu d, the mean difference, as the difference between the current year and the previous year. All right? That's how we're going to define the difference. So that when we're interpreting the difference, we know the order of those two means, current minus previous. Okay, so now that we have that, I'm going to go ahead and do my calculation to get those values. I suggest that you use Excel. Sorry. So if we use Excel, you can get the following values. So as you can see, what I've done here in Excel is that I've actually taken calculated the difference between the two sets of values. So you could see 345 minus 315, 526 minus 463, and calculated the differences for each value. A positive difference sorry means that the airfare is higher, of course. Negative difference means that the airfare was actually lower for that particular flight. Alright, so now that I've calculated the differences, it's very simple. Just this 30 is 345 minus 315. Now I could take the mean, which is the average of those values, the standard deviation, STDAV, of those values right here. And then I have the standard error. The standard error is, remember, is SD divided by the square root of n, which is 11.2. And then I'm going to actually use that data to calculate the test statistic, which I've done here in Excel, which is basically the mean, sample mean minus 0 over the standard error, which gives me a 2.05. I find a p-value of that 2.05. So basically I just use Excel to calculate all the information that I need. There's a right tail test where my test statistic is 2.05, and the degrees of freedom, because we have, actually that should be 12, not 9. This should be 12. And that should also be 12, and that should be 12. Okay, making sure I got the right set of values. P-value here, 12, and this is just ratio. Okay, great. So let's go and formulate the problem properly. And then we have these values here that we could substitute when we are ready to do so. So essentially we're going to test that the current year average is higher than the previous year average. Let's get started. So I'm going to switch over to my handy dandy iPad. All right. I'm trying to figure out where we go. All right, so here's our hypotheses. HO, HA. So the mean airfares for current year is not higher than previous year. Versus the mean for the current year is higher. All right? If we put that in symbols, then we have, if we're going to use mu current minus mu previous is equal to mu d, then we would simply say the mean difference is greater than 0 versus the mean difference is less than or equal to 0, where the mean difference is mu current minus mu previous. So that's the first step, number one. Number two, the test statistic. So remember, this now boils down to a single sample problem. And so T is equal to X bar D, the mean of the sample differences, minus mu D, which typically will be 0, over SD, standard deviation, over the square root of n to give us the standard error. The degrees of freedom is n minus 1. Now, that's step 2. Step 3, which is the decision rule. So the decision rule, you have to assume, remember, for T distribution, you have to assume the population is approximately normal. This is a right-tailed test if we look at HA. And so, this is alpha. And we were told in our problem that we're going to use a 5% significance level, 0.05. And this is our T critical. So the degrees of freedom, since n is equal to 12, then degrees of freedom is 11. Yeah. So we're going to have to go ahead and find a critical value, which would be T.05, 11 degrees of freedom. And I'm going to just sort of very quickly go over and check that out. So it turns out that our critical value is 2.71, which basically we will say if our T value, so let's just head back, if our T value is greater than or equal to 2.71, we reject the null hypothesis and file for the alternative hypothesis. Or if the p-value is less than 0.05, we reject the null hypothesis. Remember, the two rules will give you exactly the same result. All right? Now step 4, the analysis. So T is equal to, what is our sample mean? So I went ahead and calculated our sample mean. And so if we actually go back to my spreadsheet, you will see that I've calculated a sample mean of 23, right? And then I have a standard error or standard deviation of 38.85. Let me just confirm that that is indeed correct. 38.80 divided by the square root of 12. Let's make sure that's what we're doing. And so now if we go back to our formula right here, this will give us the value of our test statistic. The 23 is the sample average, 38.80 is the standard deviation, and we divide by the square root of n to find out what that t-value is. So our test statistic is 2.05. 2.05. Okay. Our p-value, because this is a one-tailed test, will simply be the probability of t greater than or equal to 2.05. If we use just give me 1 minute here, let me just make sure. just make sure I got the right value. Right tail, F6, and 11 degrees of freedom. 0.03. Okay, so I'm just making sure that my alpha value is 5%. So there we go. So I should actually make a correction here. If my alpha value is 5%, my critical value is not going to be that high. So I need to make a change. I was working with 1.1%, 0.01. So it's actually 1.795. All right? That's what our critical value is. And so I should also say $1.795. All right, so if our p-value turns out to be 0.03229, that's what it turns out to be, 0.03229. So 2.05, 0.03229. Let's look at step 5, the decision conclusion. So since 2.05 happens to be greater than 1.795, we reject the null hypothesis. If we're doing the p-value approach, we can say, or since 0.03229 is less than 0.05, reject the null hypothesis. So we conclude we have sufficient evidence the average airfare is higher in the current year. Okay, so can we be wrong? Possibility of type 1 error. Okay, possibility of type 1 error. And the probability of type 1 error is 0.03229. Okay, so that's how we would work that particular problem. If we want to get a confidence interval, say like a 95% confidence interval or 90% confidence interval, let's use a 90% confidence interval because we'll end up using the same critical value. Then what we would have to do is to just simply take the x bar d plus or minus t critical s d over the square root of n, in which case that would be 2.23 plus or minus. Our critical value is 1.795 times 38.8 over the square root of 12. And that would give us, let's calculate that. Times the standard error, that's equal to So 20.11. So plus or minus 20.11, 23. So it means that mu D lies between 43.11 and 0.89, 2.89. So somewhere between 2.89 and 43.11, between $2.89 and $43.11 higher, okay, from the previous year. So again, that proves that we do have sufficient evidence. So this is a 90% confidence interval for mu D. So I just took the problem and said, let's just find a confidence interval with the D that we have. So that's the first one. We are now going to do a sample problem involving proportions, right? All right, so let's see what we get with this particular problem. Let's take a look and see if we're on the right page here. Let's see. So there are two problems here, and okay, let's look at 1058 because of the context. I think the context is interesting. So one of the most popular economic issues being discussed recently is whether employers should be required to pay male and female employees the same salary for the same job. Data were collected via an internet site where visitors were asked to submit their votes on the issue. Compare if there is any difference in the proportion responding yes to the question between the samples of 150 men and 100 women. The number of men responding yes observed was 30. The number of women responding yes was 45. Conduct your hypothesis test at a 5% significance level. So for this particular problem, we want to look at the difference between men and women. Now, looking at the sample data, I could tell that there's a higher proportion of women who are actually going to support that motion. And so I'm going to look at the difference between proportion of women minus the proportion of men. And the reason why I took the difference in that fashion is because I'm looking for a positive difference to work with. All right? And I could tell that clearly 30 over 100 would be, 30 over 150 would be less than 45 over 100. All right? So let's grab a couple of things. So we know X for men, 30, and men is 150, which gives us P bar for men is 30 over 150, which is 5 3s are 15, 1/5, which is 20%. X women is equal to 45, and women is 100, and therefore P bar women is 45 over 100.45. So we have our two sample proportions for this particular problem. We can find a confidence interval, or we certainly can find do a hypothesis test as well. All right. So we're being asked to do a hypothesis test. Let's consider that. Now, one of the things that we need to observe with this particular problem is that the test statistic, when in the null hypothesis, HA, there is the null hypothesis. If we're going to say PW minus PM is equal to 0, or greater than or equal to 0, less than or equal to 0, then when we set the test to the boundary where we say PW minus PM is equal to 0, we are saying that those two proportions are equal to each other. In which case we're going to need a pooled sample variance. So our sample difference in proportions is going to be, what I'm saying is that we're going to have to determine a pooled sample difference, right? A pooled sample proportion, sorry. Now, I think we've been asked to test whether or not with our collector compare if there's any difference. So we're not looking so much for women being higher, we just want to know if there's a difference. So there is a difference between them, which is what we're going to try to prove, versus that there is no difference between them. So that's your hypothesis. Because stated in Woods that the proportion of men and women are the same versus they're not the same. All right? 2, the test statistic. The test statistic would be, in this case, Z is equal to P bar women minus P bar men minus 0. This comes from the null hypothesis, over P bar 1 minus P bar over N men, N women, plus P bar 1 minus P bar over N men. Alright? That's our test statistic. Our decision rule 3, the decision rule. So, is this a right tail test or a left tail test? Well, we're being asked to prove that it's just not equal to 0, in which case it's a two-tail test. And let's do that. Alpha over 2, alpha over 2 is equal to, and we're being asked to test at 5% significance levels. So alpha over 2 will give us 0.025, 0.025, in which case we have 1.96, negative 1.96 as the critical values. You're supposed to know that by now. When you have 2.5% in the tail, then we have essentially the kind of the equivalent of a 95% confidence interval, where Z is 1.96. So if our Z value is greater than or equal to, if the absolute value, since it is a two-tail test, is greater than or equal to 1.96, we will reject the null hypothesis, otherwise fail to reject. Of course, if we're doing a p-value approach, is if the p-value is less than 5%, we reject the null hypothesis. All right? Or if p-value is less than 0.05, reject HL. Very good. 4, analysis. So, we have our sample values already, 20% and 45%. So, Z is equal to 0.45 minus 0.20 minus 0. And now we have to go and find P bar. So, let's find P bar. I should have done that a little bit earlier, but anyway, P bar is X bar, not X bar, sorry, there's no X bar in there. X women plus X men over N women plus N men. Suppose that equal to 30 and 45 is 75. All right. And then we have 250. which is the 150 plus the 100. That gives us a pool sample proportion of, let's see, if we divide by 25, so that's 3/10, and that's actually 30%. Yes, I think that's 30%. So divide 75 by 25 is 3 by 10.30. So this is 0.30 times 0.7 over 100 plus 0.3 times 0.7 over 150. Let's find what that is. Calculating this in real time now. So the numerator is going to be 0.25. The denominator is going to be, let's see, the square root of, that's 0.21 over 100. .0021 plus 0.21 divided by 150, 0.0014. And 0.0021 equal, and the square root of that, 0.0591. So is equal to 0.25 over 0.0592. Okay. 25 divided by 0.0592. .25 divided by 0.0592, which is 4.22. All right. So 4.22 is our test statistic. Let's find our p-value is equal to twice probability of Z exceeding 4.22. We know the largest value we have is 3.09, where the area is 0.001. So it means that Z greater than 4.22 is actually less than 0.001. Which means that when you multiply by 2, it will be less than 0.002. All right? So this is less than 0.002. If we want the exact value, we could go to Excel. And let's see if we could get that value in Excel to work for us. Excuse me. I have a, so I think it is T Z inverse, norm inverse, NORM, norm inverse, the probability, the mean. No, I just want, so it's not norm inverse then, it's norm dist. Whoa. No. No. Equal NORM dis. Norm dis. maybe it is num s. Okay, so there we go. Our z value is 4.22. So it will be 1 minus this value. This is equal to 1 minus. So, big number. Alright, so if we actually use the function in Excel, it is called norm.s.dist. And if you say it's a cumulative value, it'll give you all the value to the left of that value. So now what you want to do is you want to find area to the right. So we're going to have to subtract it from 1, and then we have to multiply it by 2. So if I now multiply this by 2, let's see what I get. I think it's not going to show much of a difference. It is basically 2.44 by 10 to the minus 5. So the actual p-value is 2.44 by 10 to the minus 5. If we take that and we put 5 zeros in count, so it will be equal to 0.0000244. That's what that p-value is. So as you can see, it's rather small. Step 5, we have very strong evidence to support the alternate hypothesis. 5, our decision conclusion. Since 4.22 is a critical value approach, is greater than 1.96, we will reject the null hypothesis, or since 0.0000244 is much less than 0.05, we reject the null hypothesis. What do we conclude? We have sufficient evidence, or strong evidence actually, more women. So we have sufficient evidence that more women basically believe that there should be equal pay. There should be equal pay for equal work. Now, I'm not sure when that study was done, but it is possible that that could have changed over time, and now a higher percentage of men actually believe that. Now, I'm just looking here. I realized that I did not switch over. So let me do that. So this is what the final analysis looks like. Essentially, we had a critical value, test statistic, 4.22. All right. Remember, it's a two-tailed test, so the p-value is twice the probability that z is greater than 4.22, which, if we use our textbook and our table, we know that 3.09, there's 0.001 left in that tail. It's a two-tailed test, so we must multiply by 2. So we know that 4.22 would mean that the area in the tail is less than 0.001, but since there are two tails, we have to multiply by 2. So the p-value is less than 0.002. Okay? First thing. If we use Excel, the formula is norm.s. I believe it was inverse, and then you have, give it a z value and you say cumulative value is true. So what you have to do is 1 minus that, and true. So when you do that, what happens is you get the cumulative area. So in Excel, this was my 4.22, then this is the area Excel will give me, but I'm looking for this area in the tail, which is just half the p-value. And so the function again, just to write it out for you properly, is norm.s. Let me just confirm that it was inverse and not, no, it's actually not inverse, it's actually dist. So I got it wrong the first time. There we go. It's norm dist z, and if you put true, that will give us this area to the left. But if you want the area to the, so this is area here, we want the area, this area to the right, we have to go 1 minus whatever that value is that we get here, and will give us the area to the right. Okay, so that's how we would use Excel to get the exact value if we wanted to. One more thing, so if we wanted to find a confidence interval for the difference between the mean and the proportion, sorry, we would simply go P bar women minus P bar men, plus or minus excuse me, the critical value is Z, and then we would use women, P bar women, 1 minus P bar women over number of women is P bar men, 1 minus times 1 minus P bar men over the number of men. Alright? And so we now have 0.45 minus 0.20, I believe it was, or 0.30. Did I make a big boo-boo here? Let me see. No, okay, it's correct, all right. So I thought I made a bigger mistake here. I did not. So minus 0.20 plus or minus. So we're going to do a 95% confidence interval. So it'll be 1.96, and then we need to find out what's in that bracket. So 0.45 times 0.55 over 100 plus 0.2 times 0.8 over 150. All right, let's see what we got. Excuse me. Making sure that I'm looking at the right screen. So I'm actually finding out the values right here. .45 times 0.55 divided by 100 equal 0.002475 plus, let me do plus 0.2 times 0.8 divided by 150 is 0.001 plus 0.00106. Okay. Okay, let's see what we got. Mhm. Point 002475 plus 0.00106. Square root of that. Whoa, no, not true. Undo. Damn. Sorry about that. I messed up here. I pressed the wrong button. 0.002475 plus 0.00106. Add that up to the square root. That's the square root of that is 0.05945. 0.05945. That's what that is. Okay. Multiply that by 1.96. Gotta be so careful when you're doing this on a cell phone. 0.1165. That's plus or minus 0.2500. So P women minus P men is between 11 and 25 gives us 36.3665. This is 35. 2 from 5 is 3. 1. So, somewhere between 13.35% PW minus PM and 36.65%. So we are 95% confident that the difference between the proportion of men and women supporting that women should have equal work for equal pay lies between 13.35% and 36.65%. Okay, and so you can see that somewhere from the interval, the difference actually will exceed 13.35%. The same will exceed that, but be less than 36.65%. So somewhere in that range is where the difference lies. We could have tested a hypothesis for whether or not there is a difference of at least 10% or a difference of more than 10%. This interval would actually prove that for us, but we would have had to have done a test using a test statistic that looks like this if we wanted to do test that that the difference is more than 10%. So you say P bar W minus P bar men minus 10%, right? And then you would use the individual values, 0.45, 0.55 over 100 plus 0.2 times 0.8 over 150. And that's what would give you a test statistic, and then you could go further than that. Right, remember that would actually come from our null hypothesis, since we are looking for evidence that the difference is greater than 10%. So your null hypothesis and your research hypothesis would look like this. PW minus Pmen, right, is greater than 10%, versus PW minus Pmen is less than or equal to 10%. So that's where the 10% comes in to this formula. So now we do not need to calculate a pool sample proportion, because in the null hypothesis, we're not assuming that those two are the same. All right? Good. And that should do it for us in terms of an example involving proportion, an example involving match pairs. Okay, enjoy. Thank you very much.